Hello, and welcome to Polynomial Functions and Models. All right, so a little bit of modeling going on here. Let's start with a definition. The graphs of polynomials are smooth and continuous with some high points and some low points. Now, we call these turning points, and I believe I referred to turning points in my previous video on polynomial functions if you watched that. And now we'll talk about what a turning point is. A turning point occurs whenever the graph of a polynomial function changes from increasing to decreasing, or from decreasing to increasing. These high and low points on the graph are where the turning points occur and are the local minimums and local maximums of the function. Sometimes they're also the global or absolute mins and maxes. It depends on the function itself. Now, every polynomial graph has end behavior that can be described by one of two descriptions. Either both ends go the same direction, even degree, or the ends go in opposite directions, in which case we have an odd degree of the polynomial. And we describe end behavior with arrows, so we say that f of x goes to infinity as x approaches negative infinity, so the graph finishes up, and f of x goes to infinity as x goes to infinity. So it goes up, and we don't know what's happening here. It could be doing some kind of weirdness, and that's okay. The other option is that the graph has both ends facing down. So any even degree polynomial, we don't know what's going on in the middle necessarily, but just looking at this leading coefficient, a sub n, and the degree, we can describe the end behavior. Great news, I just uploaded a YouTube video and it had to tell me during this one. F of x approaches negative infinity as x approaches negative infinity. Some kind of something's going on. And then we finish by going up. And last but not least, we could finish by going down. If I was in class, I'd be showing you part of the mathematician's dance. The graph of a polynomial function of degree n, where n is greater than or equal to 1, it's a polynomial, has at most n x-intercepts and at most n minus 1 turning points. And this helps us when we're graphing with our calculator. If we could see, suppose we put in a polynomial of degree 4, and we can see all 4 x-intercepts, and we can see 3 turning points, we know we have an appropriate window for seeing the key concepts of this particular graph. We know how it finishes in the end because we could look at the leading coefficient. Let's do some examples. Use the graph of the polynomial function f to complete the following. We're going to let a be the leading coefficient of the polynomial. All right. So although I did not get the minimum in the screen, it obliterated the other parts that we needed to see. I would say, let's get our pen ready here. For part A, it looks like we have a 1 turning point, 2 turning points, 3 turning points. Number 1 will be a global minimum, 2 is a local maximum, 3 is a local minimum. Notice since both ends of the graph finish up, there will be no global max. Estimate any x-intercepts. I'm going to say a negative 1/3. Remember, this is an estimation. So we use squiggly bracket, or squiggly equal sign, saying approximately. Oh my goodness, that looks like maybe 1/6. And then maybe a half. All right, this, let's put this in green. My x-intercepts. Estimating my x-intercepts. All right, part B. Because both ends of the graph finish facing up, I would say that so if both ends finish up, it's even, right? Because it's even, it's both sides are the same. So it's A must be positive with n even. All right, we could tell that. And part C, determine the minimum degree. If there are 3 turning points, then it must be at least degree 4. It has to be an even number. We have 3 turning points. We have another x-intercept that I completely missed over here. That's 10, 8, 6. So let's not forget negative 6. You can't just ignore one of them. I see 4 x-intercepts. I see 3 turning points. I know it's an even power. I know the leading coefficient is positive. So with 4 x-intercepts and 3 turning points, I'm fairly confident that this is a 4th degree polynomial. All of that, and we still have no idea what the equation of that function is. So as we're stating the degree and the leading coefficient, that part seems easy. But remember, when we do it, we always want descending order. So we want the highest power first, and then write everything on the way down. So the degree is 3. It'd be easy to say it's just degree 2 because that's what's up here. But you have to have the highest, degree 3. Leading coefficient is a negative 1. Since it's odd, they finish in opposite directions. Because the leading coefficient is a negative, it's going to be generally going down. And for this we say f of x approaches infinity as x approaches negative infinity. And down here we say f of x approaches negative infinity as x goes to positive infinity. This function is already written in descending order. All right, so x to the 4th is our leading term. So we know we have degree 4, which tells us both ends finish in the same direction. Our leading coefficient is 1, unwritten 1 in front of the x because it's positive. I know my end behavior, with whatever goes on in the middle, the end behavior, degree 4, they finish together. Positive, they finish up. So we say that f of x approaches infinity as x approaches negative infinity, and f of x approaches infinity, woo, that one's a crazy one, as x approaches positive infinity. All right, so end behavior, if you draw the little diagram, it's easier to write what the actual end behavior is with the arrows. All right, second concept in here is piecewise defined functions. Now, we're going to look at specifically piecewise defined polynomial functions in this particular section. And really all it means is this function has different portions of the graph for different domain values. All right, so like when you're a kid, maybe they called you Jimmy. When you were in high school, maybe you went by Jim, and now that you're at work, maybe you're going by James. It's just three different names, 3 different outputs, depending on what time of your life or what time of the domain that you happen to be in. That's all a piecewise defined polynomial function is. So if I want to evaluate f of negative 3, what I have to do is I key in on the negative 3. If I use an x value of negative 3, I'll use this portion of the graph, or excuse me, of the function. All right, negative 3 input. Negative 3 cubed is a negative 27. Negative 3 squared is 9. Negative 27 minus 36. 20 and 30 makes 50. 7 and 6 make 13. So this is a negative 63 output. I gotta find colors that go nicely with purple now. If I want to evaluate a f of 1, I key in on the x value and I ask myself, is 1 less than or equal to negative 3? No. Is 1 between negative 3 and 4? Yes. Yes, it is. So I will use this piece of the function. I'll input 1. 3 times 1 squared is 3 times 1, which is 3. Give ourselves a little more room here. Finally, if I want f of 4, is 4 less than or equal to negative 3? No. Is 4 between negative 3 and 4? No, because there's no equal to sign. 4 is greater than or equal to, in particular, it's equal to 4. So we'll use our brown to do something cubed minus 54. 4 cubed minus 54, that's 64 minus 54, which is 10. So we can evaluate the function. The input tells us which piece of the formula that we want to use. All right, so we're going to keep that in mind as we sketch this graph. Now, if I want to sketch this graph, I'm going to assume it's continuous. I want to determine if it's continuous. So let's put my graph over here. It's going to be quick and dirty. It's going to be rough and ready. Oh, I did a bad thing. There we go. There's -5. I only need to go up to 2. I have no idea how high or how low I need to go because I have not evaluated my function yet. So let's just give this a shot and see what happens. So I'm going to do the top piece. So x and 2x. It's a polynomial. It's linear, actually. So I'm going to use -5, -4, and I could use all of the values all the way down to -1. But here at -1, notice there's a no equal to. So I'm going to put an open circle to remind myself that I cannot equal -1, but I could get super close within a little circle of it. -5 has an equal sign, so I'll use a solid dot. When I evaluate, I get -10, -8, all the way down to -2. So it looks like I will probably need to use a couple of these values. -5, -10, that's going to be up here somewhere. And we'll label it. That's probably not going to be up there somewhere. Let's make sure that's negative. And what we can do, actually, let's make our y-axis go by 2. Little cheater's method there. -5, -10. We know it's linear, so we know it's going to be a line, so I'm going to jump here to -1, -2, and we graph it. And that's it. That's it for that portion, so we stop. We only draw that graph between these values. Now our next piece, x and -2, -1 we can use, and 0 we cannot. So I'm going to use a little open circle. But we get -2 out either way. So this is -2 from -1 to 0. Let me see, I'm going to fill this in green, open the circle, there. Finally, we find the piece of the graph that is x squared minus 2, only for x values between 1 and 2. Notice these are equal to's, so I'm going to put little solid dots. I only care about the endpoints. All the other points are going to be solid dots. Only the endpoints could be open circles if there's a not an equal to option. Evaluating, we get 0 minus 2 is -2, 1 minus 2 is -1, and 4 minus 2 is 2. So I'll have 0, -2, so I could fill in that hole. 1, -1, and 2, 2. And we know this is quadratic, so we know it has the shape of a parabola. And what I did right there was wrong, so I'm going to take that off. What did I do wrong? This graph stops at 2. So I'm always telling students, don't forget to continue your graph on, but in this case, it stops. All right, and with the different colors, you can see I'm only graphing between -5 and -1. I'm only graphing between -1 and 0. Only graphing between 0 and 2 for each of the pieces. All right, let's do an application problem. This is going to be the last example. The table lists the number n in thousands of Americans over 100 years old for selected years x. We want to use regression to find a polynomial of degree 3 that models the data. We're going to let x equals 0 correspond to 1960. So when we enter data, first thing we have to do is turn on our calculator. I'm going to go to Stat, and I'm going to Edit. In List 1, I'm going to put my x values, but I'm going to adjust them. X equals 0 corresponds to 1960. So this first one is 0. and then 10 years later, 20 years later, all the way up to 50 years later, which is 2010. List 2 will be my n values, 3, 5, 15, 37, 50, and 70. Make sure your lists are of the same length, or else things are going to get really kind of weird. So we want to use a regression equation to find a polynomial of degree 3. I'm going to quit out of here. Press stat. I'm going to calculate cubic, right? Cubic is third power. I'm going to use list 1 as my input, list 2 as my output. I'm going to store my regression equation. In order to do that, when I arrow down, I go to variables. I arrow over to y variables, select function. I'm going to put it in y1. And then I ask it to calculate. And so here we have a polynomial of degree 3. And it looks like this will be y equals negative 6.296 x cubed plus 0.065 x squared minus 0.368 x, and my constant term is 2.817. I rounded to 3 decimal places. Now I can graph, if I go to the graph here, that's going to be a negative 10 to 10 window, so it's going to give my cubic this whole time. But remember, we went all the way up to 50. You could go to zoom, and I'm going to go up to take me to the bottom. And I'm going to go to zoom stat. That was a horrible selection because I forgot to do something very important. I need to turn my stat plots on, so it'll plot those. Now when I go to zoom stat, it'll plot my dots and the part of the curve that actually matters. Notice that's pretty close. That's a pretty good regression equation in the same window. So we could take this and input it here, but since it's on the same screen and this is a recording, I'm not going to write it down for you. I'm going to put a C graph. Estimate n for 1994 and 2019. Well, I know that 1994, 1660, huh? That's been thinking too much about my history of math class. 34. So my x value will be a 34. What I can do is I can trace, and I'm going to go down to the curve, and I'm going to input 34. It looks like it'll be 41. Let's call it 41. N equals 41,000 Americans over 100 years old. Be sure to include the units, thousands. It's not just 41 people over 100 years of old, 100 years of age. It's 41,000. That's good news for those of you that want to lead a long life. 2019. Let's see. 2019 minus 19. I did it again. 1960. 40 years. If that's 50 years, it'll be 59 years, right? So I will need to expand my window a little bit because my window only goes up to 55. I'm going to take it up to 60. Look at the graph again. And I am going to trace the actual graph. I'm going to input a 59, and it will tell me, in this case, that n 79.6, let's call it 79.6 thousand people over the age of 100 last year in America, according to the estimate. Notice that this is, the 2019 is outside of the range. This is an extrapolation. It's outside. Whereas the value of 1994, it's in the data set, so this is interpolation. And that's it for this video. Thanks for listening.